Good evening. It's 6 o'clock, and we're going to begin the program tonight. On behalf of UC Health, my name is Chiara Delmonico, and it is always so exciting to see a room full of people here to learn tonight. We ask you to fill the survey out at the end, but it's really important to us that you take time and fill out the post-event survey so that we can be assured that this program will continue. We're very excited that Dr. Santoro, Dr. Cornier, and Dr. Huntington-Potter are here to give their life lessons in pearls of wisdom for you tonight. It's really a tremendous gift to get this education. And we expect that what you learn, you go home and teach your friends and family and be good guiders to healthcare. Dr. Regensteiner?
Hi, I'm Judy Regensteiner, and I welcome you on behalf of the University of Colorado School of Medicine Center for Women's Health Research, where our mission is to do research in women's health in regards to cardiovascular disease, diabetes, and mental health, and to mentor the next generation of young scientists who do work in women's health and sex differences, and to educate the public and healthcare providers. So with that mutual mission of education, we are here.
We are here today. Thank you. So we've been presenting Let's Talk since 2011, and it's 2017. So we're doing some good work. Thank you.
So our first speaker is a close colleague of mine with whom I'm very privileged to work, Dr. Nanette Santoro, who's the E. Stewart Taylor Endowed Chair of the Department of Obstetrics and Gynecology at the university here. And she is chair of the department, and we're very proud of her many accomplishments, which include almost constant funding by the NIH for over 20 years, or maybe more, and work both in mentoring and in her research. She excels very, very highly. Her area of focus is the menopause, which is a little unusual, I think. When I think of OBGYN, I don't automatically think of the menopause, but I like her approach, and I think it's very innovative. Dr. Santoro is a co-PI with me on a major grant, a training grant, to train young researchers who want to become researchers in women's health and sex differences. And she also has a grant training young OBGYNs to become researchers. So she has a lot of duties, and I'm always impressed by her generosity and willing to work on important things together, and she's just an excellent colleague. So without further ado, I will welcome Dr. Santoro.
Thank you. Can everybody hear me okay? All right. So I'm here to talk to you about something that you're probably all recognizing and maybe just feeling a little bit right now, because Thanksgiving has ended and we've all managed to eat our way into at least one coma over the past 4 days, because that's what Thanksgiving is all about. And Thanksgiving and menopause work together to steal away your waistline. So what I want to talk about in the next few minutes are some of the things that happen to give you an idea of why is this happening to you. You're not the only person it's happening to, and a few things you may be able to do about it. These are some of my disclosures. Both of the companies I consult with have treatments for hot flashes. And I haven't really gotten any money from them yet, so doesn't change what I'm going to tell you. So what I want to go through with you are what are the stages of the menopause transition, what is happening at each of these stages, because the stages turn out to be important, because that's when you can predict or expect symptoms to happen. So which ones are going to be most associated with those symptoms will be helpful. Apart from menopause itself, what is due to aging? We all like to blame it all on menopause because then we don't have to think about aging at all, but aging is happening in the background all the time. And that's also changing physiology and changing metabolism. So looking at some of those age-related processes is really important. And finally, what can you do? So this is the road to menopause that you can see on this slide. So prior to the transition into menopause, women have regular cycles, and the reserve in the ovaries, the number of eggs that are left, is normal, which was within a pretty wide range. When that number of eggs gets down to about 1,000 from a starting point of 500,000 at puberty, with the woman's first period, she begins to skip a cycle, and that's the early menopause transition. The median age that happens at is 47, but it can be very variable. And this isn't another important point to consider, is that the earlier it happens in life, the longer the transition. So how many of you know somebody who said childbirth wasn't that painful for her? And really, like, thank you so much, thanks for telling me that. There's some women that say, oh, menopause was no problem for me. I was 53 years old and I just didn't have any more periods. And that may happen. So a woman who gets her last period late in life may have a shorter time through the chute of menopause or of the transition with less symptoms. The woman who starts this at age 35, she's in for a long, ugly ride. So she's going to have more symptoms and is likely to have a longer period of these skipped cycles. And I'm going to show you why, when you see the hormone patterns, why that can be more, it's going to be more symptomatic. So the early transition is at least one period in the last 3 months. So when a woman is cycling enough that she's having at least one period in that 3-month length of time, she has enough estrogen around. So usually she's not going to get a lot of symptoms, but symptoms will tick up a little bit. So women who are going to be the big bad hot flashers are going to start to have them at this point. By the late transition, when median age of 49, but again very variable, menstrual periods are 3 to 11 months apart. So that's much longer periods of time without estrogen and no periods, and that's when symptoms really start to get much more pronounced. They get more severe and they get more frequent. So the late transition is really the hot spot. That's kind of the speed bump on the road to menopause when women are likely to run into the most trouble. And these are the 7 dwarves that tell you what you may be experiencing. So I'm told I can only show this slide because I'm a woman, and I will gladly take that privilege. Hot flashes, sleep disorders, vaginal dryness, mood issues, and some women will experience something that they kind of describe to me as brain fog. And some of that may be hormonally related. It's not so clear. And some women will also report a change in their sex drive. And again, not clear if that's so hormonally related. It can also just be related to problems with sleep and all the other aggravations that are just not making you feel all that sexy at this particular time in life. But the symptoms you can really attribute to menopause are really these top 5, which are mood, sleep, hot flashes above all. About 85% of women will report having hot flashes, and the other 15% I think are liars. So what kicks the vicious cycle off is not clear, and some doctors are doing very interesting research on this because they're taking younger women in their 20s and 30s and giving them a medication to abolish their reproductive hormones to kind of give them a medical menopause and see what happens. And there does seem to be some relationship that's a little bit of a cascade. So it's not clear exactly where the circle starts, but let's start it here with that late transition when women have low estrogen levels and they start having hot flashes. And what do? They wake you up at night. They make it harder to sleep. So your sleep starts to become something that you can't count on. And if you're a champion sleeper like I am, this can be very unpleasant. You're not sleeping well. You don't do so well in the daytime. If you sleep-deprived people, what do they do in the daytime? They move less and they eat more. So exactly what you don't want to see happen to compensate. This leads to weight gain and inflammation, and Dr. Cornier is going to talk a lot more about that. The weight gain, we have shown from studies of women as they go through the menopause, leads to hormone changes that favor more weight gain. And the weight gain itself actually makes hot flashes worse, as does the probable increase in inflammation. So it's kind of a feed-forward cycle that some women can get into that can make menopause pretty unpleasant. And that's how it starts to add the rings to you that happen. So one of the other hits that happens, and this is not just menopause, but is also related to age, is that the metabolic rate drops. it can drop as much as 25%. So let's all take a deep breath and exhale and let go of that 25%. 25% is almost an entire meal. And I can't tell you how many patients I see who come in very aggrieved that their weight is going up and telling me, very clearly that they monitor their intake, they know they're not eating more, they're eating exactly what they were eating before, and I have to tell them that's the problem, is that you're eating exactly what you're eating before. You can't do that anymore. You either have to expend more calories or take in fewer in order to compensate for that drop in metabolic rate. And for some women, this is abrupt and happens in the mid-40s. For others, it's a little more gradual. For men, this is a much gentler, slower process that begins in their 20s and decreases over time. But women seem to have a bigger drop. So basically, this means you can't continue to consume the same amount of calories and expect to stay where you are. Who's tried dropping their calories by 25%? Who's tried low-calorie diets, grapefruit diets, coffee, whatever, crazy smoothie diets? And it's hard. It's very hard to do. So much of the time, you may try to make it up with activity. So eating 25% less, about 400 calories, cuts out almost an entire meal. And increasing calorie expenditure by 400 calories, that goes over a little better in Colorado than it does in other states. In New York, I think my patients used to want to throw rotten tomatoes at me when I would tell them this. But this is what you have to do to burn that 400 calories. Walk for an hour, dance for an hour, 40 minutes of tennis, half an hour of stationary bike or elliptical, or a half an hour of running at a gentle pace of 9-minute miles. So basically, here's the Red Queen dragging Alice along, saying it takes all the running you can do to keep in the same place. And that's a little bit of what happens. And if you get behind in this and you keep getting behind, you get into the feed-forward loop that I was showing before. So it's helpful if women get on top of this early in the process to arrest that. When you're in the middle of the transition and you're having the worst symptoms and you're really not sleeping and you're really having a lot of hot flashes and we can't relieve that quick enough, it can be very hard to undo some of that. So there is a relationship between sleep, weight, and metabolism. It's very complex. Hormones are playing a role, and again, probably estrogen is playing a big role. But poor sleep is related to the metabolic syndrome. Who knows what the metabolic syndrome is? Do you want me? I can explain it. It's just thick waist, higher blood pressure, and abnormal blood lipids. So all of those things predispose a woman to diabetes and heart disease. And metabolic syndrome, also you're insulin resistant. So you have high insulin levels. Your body, it favors more weight gain. So just that change in sleep can begin some of the alchemy that leads to a lot of these other problems. And the further weight gain, again, favors the hot flashes, and you can also develop other sleep problems on top of that, like sleep apnea. And then your sleep even gets worse. So here's the metabolic syndrome. Waist circumference of 35 inches or more in a woman. And if you are Asian and petite, you have a smaller waist circumference will get you there. Elevated triglycerides, low HDL cholesterol, blood pressure over 130/85, or a high fasting glucose over 110. So those are the definitions of the metabolic syndrome. It's 3 of the things on that menu. So if you have that already, going into the menopause transition, it's something that it's really helpful to try to control and be very diligent and careful about it. So menopause can take this metabolic hit and make it worse. 61% of midlife women have insomnia. Women are overall worse sleepers than men. And then you have night sweats waking you up. Sleep can also get worse due to other issues. So if you snore, I usually need a spouse or significant other in the room to tell me that my patient snores, because my patients will never admit it. You might need a sleep study to see if you need something to deal with that. That may improve sleep and may help reverse some of the weight gain. Restless leg syndrome, maybe 16% of people have that, an irresistible urge to move your legs at night, so your legs may be kicking around. Not only is that going to wake you up, it's going to wake up your bed partner, and they're not going to be happy with you. And anxiety and depression, both of which may be menopause related, will also contribute to poor sleep. So that goes along with it. Difficulty falling asleep or waking up and then not being able to go back to sleep. And with depression, you can also wake up early and not be able to go back to sleep. So if mood is becoming a problem, that's also an issue that needs to be attended to. It can be associated with menopause. So there's an increased risk of depressive symptoms. If you measure depressive symptoms, which is something you do on a survey, that's not the same thing as major depression. About 26% of women have depressive symptoms go up, and major depression only happens to about 15%. But a very important thing about this, and you may see this in yourself or in friends that are going through menopause, is the biggest increase in depression are not the women who have had depression before, it's the women who've never had prior depression. So it can hit you like a ton of bricks, and you may not even know what it is you're dealing with because you don't have a vocabulary for it. We've done, one of the studies I'm involved in is the SWAN study, which has been going on now for 25 years. And we've looked at women as they went through the menopause transition. And let me tell you, in the beginning, they were 45 years old, and every year their mood got worse and worse and worse. And I kept thinking, where does this end? Oh my goodness. And then after menopause, it gets better. So it doesn't keep getting worse, which was good. It was a reason to go on and keep doing this study and not be so afraid of my own menopause. But it can be rough for some women. And the same thing is true for anxiety. So women that have had chronic anxiety, they're not a problem for me in the doctor's office because they'll come in and they'll say, my anxiety's acting up again. But a woman who's never had it before doesn't know what to tell me. She may have palpitations, she may have other symptoms, and it may take a while to figure that out. So it's a good time when your friends may be able to help you diagnose yourself. Adverse mood is also going to activate stress hormones, increases cortisol. Everybody knows from the popular literature, what does cortisol do? Helps you gain weight. So none of this, all of this conspires. So you see how it's all going after your waistline. So depression and anxiety states activate the adrenal gland. So instead of the normal rhythm that you have where it rises in the morning when you get up and you're busy and it goes down at night and helps you sleep because you're less activated, that timing gets off. So that low afternoon drop stops happening and it kind of tends to stay higher and again will make it more difficult to sleep. And what happens when you can't sleep and you're stressed? Welcome to the holidays. Let's put people with their families all together with a lot of dessert. So when you stress animals, they go straight for the comfort food. So we're designed to do this. If they're given free access to food, they go straight for the salt, the sugar, and the high fat. So Dr. Cornier is going to tell you all about how to not do that, right? But it's what we do. So you get a lot of information thrown at you. I'm giving you a lot now, and I've given you the whole setup here, but what can you actually do? I want to spend the rest of the time talking about some of the strategies. How do you deal with that dropping resting metabolic rate? Well, you do have to figure out some ways to eat less. Women are generally good at restricting. We've always been on wackadoo diets at some point in our lives. So there's different ways to trick your palate, try new foods with low-calorie choices, and eat food that looks like food. Has anyone read Michael Pollan's book, An Eater's Manifesto? It's great. It's like 3 sentences. Eat food, not too much, mostly plants. Work out more, trick your body again, whatever works. Use everything in your toolkit and find new activities if the ones that you're doing become a problem. One of the other issues that happens to women sometimes in menopause are joint aches and pains, and that can make you stop working out, or you may get an intercurrent injury, so you may need a repertoire. If you're not a versatile exerciser. My husband is a runner. He will only ever run. He will never do anything else. If he ever gets any injury, he's just out of commission. Find another thing. How do you treat poor sleep? If you're having a lot of hot flashes and night sweats, hormone therapy is a very reasonable alternative. I'm going to talk a little more about it. And if you don't want or like the idea of hormones, there are a number of non-hormonal alternatives, and there's actually some very exciting medications in the pipeline that may be coming available as well as that are completely non-hormonal to use to deal with that. For sleep apnea, we have the treatments of CPAP, which is the nasal cannulas. I'm sure you've all have friends that carry those around. And weight loss, restless leg syndrome, gabapentin is one of the drugs that can be used for that, and that's also a very effective drug for hot flashes at night. It makes you sleepy and drowsy, so that's why you don't move, I guess, but it also can be helpful for hot flashes. There's also cognitive behavioral therapy. CBT now is the big thing for just about everything. It's going through a real heyday, but it's actually been shown to be quite effective. And there's a self-guided CBT app. It's called CBTI for insomnia. And it was invented, I think, by the VA. It says Veterans Administration on it, but you can get it at the App Store, and it will guide you through a bunch of CBT exercises that you can do to customize your own program to help deal with insomnia. And many of my patients find that effective. It is as effective as some medications. So if you can stick with it, it's a very helpful behavioral method. Some of the metabolic challenges may not all be your fault. Some of it may be in your genes, and you may need other therapy for it. So pre-diabetes may be treatable. So get tested. This is a time when I do have patients that are gaining weight. We'll check for any pre-diabetic states, or actually sometimes pick up an early case of diabetes. So lifestyle or medication can be used. Usually that's a low glycemic eating pattern and more exercise. You're getting the theme. I keep talking exercise. And metformin or glucophage can sometimes be extremely helpful for some women, especially those who are just beginning to acquire some of those metabolic syndrome type problems, because it can facilitate weight loss and will make them more insulin sensitive. It's not for everybody. About half of my patients tolerate it, but for those who tolerate it, it can be really an excellent choice. Will hormones help? Well, the short answer is maybe they'll help with metabolic issues. You can definitely try them. For many women who have other menopausal symptoms, a brief trial of hormones doesn't commit you to a lifetime of them. 3 months will tell you if they're working or not. And if they're not working, there's no reason to continue them. And hormones can be given in a number of different ways. All of the major medical bodies that talk about hormones or have statements or evidence-based practice guidelines, the Endocrine Society, the North American Menopause Society, all of these websites have good sources of information as well. The American College of OB-GYN all advise women to take FDA-approved prescription hormone therapy. So you've heard phrases tossed around, bioidentical hormones. It's all over the internet. I live with this every day. It's been going on for like more than a decade, and I don't know what it means. Bioidentical is not necessarily a meaningful phrase to the extent that it means a hormone that's identical to what your body would produce. Those are now all available in FDA-approved forms. So unless you're allergic to every single hormone that I can possibly give you, there really isn't a logical reason why bioidentical hormones are better. They're very heavily advertised. It's a lot of direct-to-consumer advertising. But when you take them, you're taking something that has not met the same standards of efficacy and safety that the FDA requires to approve a hormone. So the FDA recommends against it as well when they go and test the hormones, because they're mixed up in a cream. Absorption can be variable, and sometimes the amounts of hormone can vary greatly. So you're taking a risk with yourself by using them. Now, we all use them. All endocrinologists use compounded hormones at some point or another, because we have patients who literally can't take anything. that I can give them. They're allergic to all of the things I give them. So, usually you're in the ballpark, but, ultimately you don't know. Why would you do that if you know you can get something that's just as natural? So, compounded hormones, estradiol and progesterone, the steroids are stable. They're pretty easy to mix and weigh, and a good pharmacist can certainly do this. But the creams and gels can vary. So if you're rubbing it into your skin, it's not at all clear that your body's going to absorb it. It has not been tested. Some of the websites you may see recommend salivary hormone testing. There really isn't a logic behind that. There's really not evidence to back that up. What's the right level of hormones when your symptoms are the indication? If you're taking it, you have the right level, but you're still having hot flashes, you're not taking the right amount. So the saliva also, when you are taking these hormones, doesn't reflect levels in the bloodstream. So the bloodstream is really what we as endocrinologists think matters. That's kind of the definition of a hormone, is it travels from where it was produced to where it has action. So evidence-based hormones are pharmaceutical grade, they're FDA approved. They are just as natural, they are chemically identical to what's made by the body. And the medication dose is adjusted across a wide range to treat the symptoms. So you, the patient, are the arbiter of success. Are your hot flashes better? Are you sleeping better? If not, let's try another dose. It isn't necessary to measure hormones all the time to make sure that they're working, because they've been tested in hundreds to thousands to maybe tens of thousands of women, and we know what they're doing. So I can't end the talk with bioidentical hormones without talking about Suzanne Somers. She's the spokesmodel for the whole bioidentical hormone movement. And if anyone had told me that I would be trying to argue scientific legitimacy with Chrissy from Three's Company and have a problem actually proving my case, I would never have believed you. So, life is strange and wonderful. So we live in a world of alternative facts, and I think you should beware the alternative facts. Bioidentical hormones became available in part because there was a loophole called the DSHEA Act, Dietary Supplement Act of 1994. The Obama administration tried to correct this in 2013 with the Compounding Safety Act, but to my knowledge, this has not changed anything. But that legal loophole has made these hormones, which are powerful substances, considered dietary supplements, which makes no sense to any of us, but the FDA has not stepped in and only steps in if damage is done. So these are very aggressively marketed substances, and I view this as being a predatory practice. It's so successful that up to a third of all hormones prescribed for menopause look like they may be custom compounded. So a third of women taking hormones for menopause are taking unregulated stuff. That seems crazy to me, but that's where the world is. A lot of things seem crazy to me lately. And there's virtually no medical evidence about what these hormones are doing. So you're basically performing an experiment on yourself by taking them. And the absence of evidence is not the same thing as evidence of absence. So if there's no proof of harm, it's just because there's no proof. There's just no information out there. So how do you sort all this stuff out? There are a number of different ways that you can get help. And to deal with alternative facts, I vastly prefer facts. So these are some of the resources and places where you can get information. The North American Menopause Society has just published their guideline, and they have very, very good consumer information. The use of hormones, non-hormonal alternatives, and other combination treatments, as well as behavioral treatments, are all covered in different patient materials that NAMS promulgates. Very easy to get at. Also very good information on women who have had hysterectomies, so medical treatments for them as well, because it differs and the risks differ. The SWAN study is the study of women's health across the nation, has been studying women for 25 years as they go through menopause, and that has very good information on health risks. We also have a website for SWAN. The Endocrine Society has the Hormone Health Network that has a menopause map that you can use that takes you through what are your symptoms, what are your health risks, are hormones a good idea for you. And the Ms. Flash Network is a clinical trials network that publishes the results of randomized trials. They have done results on cognitive behavioral therapy. They've done results on omega-3s. They've published results on a variety of antidepressant medications for hot flashes, and they have a very useful, easy to navigate patient site. And the Red Hot Mamas are a fun organization as well that provides information for consumers. So don't go it alone. And we can all survive this. But this says menopause when it feels as if your brain has too many tabs open and you can't find the one playing that annoying song. So with that, I thank you for your attention, and I will let Dr. Regensteiner welcome the next speaker.
Afterwards, and I really enjoyed that talk very much. Our next speaker is Dr. Marc Cornier, who is an endocrinologist and researcher at the University of Colorado and is medical director of the clinic at the Anschutz Health and Wellness Center. His research interests include understanding the complex regulation of food intake and body weight. He studies how and why we eat and how this relates to unhealthy weight gain. Thank you, Dr. Cornier.
Great. Thank you. Thank you, Judy. Thank you for the introductions, and thanks for the invitation to come chat with you guys tonight. And thank you all for coming tonight. I know it's getting cold out there, and I didn't bring a coat. So we're nice and cozy right now. So I am, as Dr. Regensteiner mentioned, I'm an endocrinologist. I see patients, so I am a clinician, and I see patients here at the hospital in the endocrinology clinic and in the lipid clinic through the cardiovascular center. I also see patients at the Anschutz Health and Wellness Center, where we primarily work on weight loss. But I'm going to wear tonight my scientist hat, my researcher hat. So if we have more clinical things we want to talk about, we can do that in the question and answer at the end. But I'm going to talk a little more researchy, a little more science tonight. And we'll talk about why do we eat? You know, some of the questions of Thanksgiving. Remember, we talked about Thanksgiving at the beginning of the first talk, and why did we eat so much at Thanksgiving? What's going on there? So I think it's important to understand that why we eat has a biologic reason. There's reasons for it, right? Our body wants us to eat, but there's also other reasons, and so we're going to get into that and how those things interact. If you have any questions, please don't hesitate to ask me at the end. If you're too shy to ask questions, at the end, I'm happy to give my card and information, that kind of thing. All right, so the science of appetite, that's kind of what we do. And this made, Time Magazine, this was pretty exciting. We got to share our science. Well, it wasn't my science, but it was our groups across the country's science with Obama and George Clooney. So that's pretty exciting when I saw this. And you read it, it says, why we're hardwired to crave the wrong things. And I think this is actually wrong. We're not hardwired. And that's what I'm going to show you tonight, is that we can actually unhardwire things and change it. So it's not all hopeless. So we are going to talk about this exactly. All right, but I am a clinician, so I like to start things with a case. All right, so JS, she is a 58-year-old woman who wants help with weight loss. Yay, that's the first step, right? You gotta want to do it, and you have to be motivated. She reports slow, gradual weight gain over time, but this was especially a problem after her pregnancies and now after menopause, as we heard about. All right, most of her family members are overweight, so there seems to be a genetic component to this. She's tried every diet out there. She can teach me about all the diets. She doesn't understand why she's gaining weight, so she exclaims, my metabolism must be low. And we hear that over and over again. And what we heard is maybe she's right to some degree. Maybe as she's gone through menopause, her metabolism is lower than it was. All right. I don't eat at all. I hear this from most of my patients as well. And I do what's called a 24-hour recall. I ask her, well, what did you have for breakfast this morning? What did you have for lunch? And we go through what she ate the last 24 hours, and she's not eating anything. At least that's what she's reporting to me. She says she doesn't really eat out of hunger. Well, so some people eat out of hunger, some don't. She doesn't really get emotional. She doesn't snack a lot. She doesn't drink beverages with calories. She's doing all the right things, right? So she works out. She goes to the gym a few times a week. So that's great. So what else can I do? She says. All right. She's very frustrated. So a couple of things. My metabolism must be low. So is that true? And the reality is, I know that's probably not the case. It might be lower than when she was, maybe premenopausal, but still the reality and the research would support the bigger you are, the higher your metabolism is. Because your metabolism is driven by your muscles and your other organs. And the larger you are, the larger your organs are, the more muscle mass you have. And so your metabolic rate actually follows with your size. Now, not everybody's the same, but certainly in general, I can't say confidently that your metabolism is low and that's why you're gaining weight. And also, there's really nothing we can do about our metabolism. There's no treatment in this 2017 that raises metabolism. So that's frustrating too, but we have to get a handle on that. All right, I don't eat at all, right? That's what she says. You know that she has to be eating because she's gaining weight, and her metabolism is probably not low. So to gain weight, she has to be consuming more calories than she's burning every day. So I know she has to be eating more. So is this her true perception, or does she feel bad and doesn't want to let me know what she's eating? And I really believe that this is her true perception, that she doesn't understand how much she's eating on a day-to-day basis. She doesn't eat out of hunger. Well, if she doesn't feel hungry, then why does she start eating? What signals her body to eat? What signals her body to stop eating? We know she has to eat in excess, at least relatively, or else, so the question I have is, what's regulating all this? All right, is her biology really the fault for her weight gain? Is it all biologic, or is it behavioral in nature, or is it a combination of these things? All right, so we know that rates of obesity have gone up dramatically over a fairly short period of time, decades here, right? So while genetic factors are really important, our genes and our genetics have not changed in 30, 40 years where the obesity rates have gone up. So genetics is not the cause of our obesity epidemic. So the environment really has to be the culprit. And we know that there's tons of good, cheap, high-calorie foods out there. And we know that our new environment is to be less active, right? We can look at the workforce, we're much less active, all our electronics, cars, everything, right? So favors less activity. So likely, our genetics makes us prone to weight gain, and we're in the wrong or right environment to cause that weight gain. We also look at the biology, and we'll go through some of this, is really designed to protect us as an organism from undereating, from undernutrition and starvation. So most of our signals are really getting us to want to search and seek food and eat food when it's available, or else we would die. And so it makes sense that our biology really promotes and protects us from undereating and undernutrition. And so it's not set up for the environment that we live in today. All right, so 2/3 of the country is overweight or has obesity. That means 1/3 of the country, of people in our country are normal weight. So why are some people normal weight? Why isn't everybody having trouble with their weight? So we're interested in that, and some of our research is based on that concept. So we want to know how our genetics and our biology interact with the environment. At the end of the day, as an organism, we want to be in balance. We call that energy balance or homeostasis. So we want the calories that come in, whether that's food or beverages, and I'm going to call that energy intake, not just food intake, because we can get the energy come in liquid form too. That's not really food. And that needs to be in balance with the energy that we burn in a day. And the energy we burn in a day comes really from 3 places. Our basal or resting metabolic rate, which is really determined by our body size for the most part. Digestion burns a little bit of calories, but not anything dramatic. And then we have activity, which is our biggest variable from one individual or day-to-day basis. When these are equal, our weights will stay stable. And most of us stay at a pretty stable weight for most of our lives. So the system works pretty well for most of us. Now, if energy intake goes up, energy expenditure goes down, that energy has to go somewhere. It's the laws of thermodynamics, if we go way back to chemistry a long time ago in high school. That energy can't be created or neither created or destroyed, right? That's the one. And so if there's more energy coming in than it's been being burned, that energy has to get stored somewhere. And it gets stored as adipose tissue or fat on our body. All right, so there's this whole point, or theory about a set point. And it comes from data that comes from animal studies. And I think this is pretty interesting stuff, so I'm going to share it with you. So these are experiments done in rats. Rats aren't humans. Rats keep growing over time, which is it was an issue when we're trying to generalize to humans, but certainly it's an important experiment. So what we see is rats are on a trajectory for their weight. And this is this line B here. They're given free access to food, and over time, they gain weight on this level. This is their body weight here on the y-axis. Now, at point 1, they're either given more food or they're given less food. And at point 2, they're allowed to free live and eat whatever they want at that point. And so what we see is when animals are force-fed, they gain weight. But when you let them do what they want to do, they start losing weight and they go right back to where they would have been had they been allowed to eat whatever they wanted. So that's why we call it a set point. And the opposite experiment was done. They're food restricted, so they lose weight. And at point 2, they're allowed to eat whatever they want. Well, they regain the weight and they end up right at the same place as their counterparts here on this blue curve. Pretty impressive. And so this has to be biologic in nature in terms of what's controlling that. All right, do we do this? Do we humans do this? And so there's been some experiments of chronic overfeeding. And there's 2 really good ones. There were weeks and months long where they made people overeat by thousands of calories over weeks on end. And so what these experiments have shown is that, yes, as humans, we also adapt to some degree. And how do we know that? Is that we can, if I tell you to eat 1,000 extra calories every day, I can calculate how much weight you should gain. And what we find is that people don't gain as much weight as they should, by about 25 to 30% on average. But there's also this significant inter-individual difference between one person and the next. And so one person may gain 80% less weight than expected or predicted, and the next person might gain 20% more than predicted. So there's a lot of variability there, so there's something going on there. All right, so there's some adaptation. So how might we adapt? So it might be all genetically driven, and that's certainly potentially true. We certainly, when we overeat, we could then burn more calories, right? We could increase our energy expenditure. There's really not much, we do increase our metabolic rate a little bit as we gain weight. But we also might increase our activity even without knowing it. We could change how we metabolize fuels, so fat and carbs and proteins, so with that we could burn more fat or reduce the absorption of nutrients. That might help protect us. Or it might all be on the intake side. So we might have changes in hormones that relate to appetite, and so we're less hungry after we've been overeating, and we compensate by eating less after the fact. Or it might all be cognitive or behavioral in nature, or a combination of those things. And this is what we study in our group. All right, so how is food controlled, food intake controlled? So one is there are physiologic mechanisms, biology that drives this. And we know that there are hormones and neurologic signals that are meal related. So meal to meal, day to day, that tell you to eat or not eat. So they tell you be hungry, be full, that kind of thing. We also know that there are, back up, long-term signals. So our body can sense how much body fat it has and therefore potentially alter how you eat down the road. But we also know that there are non-physiologic mechanisms that drive us to eat. So reward and motivation, cognitive things, environmental cues, and the social context, just to name a few. All right, here's an example of some of these signals. All right, in 1994, it was discovered that fat cells, adipose tissue, makes a hormone. So forever and ever and ever, we thought that adipose tissue was just a place to store fat for later use, to have energy for later. But it was discovered that there's actually a hormone produced by fat cells, and that hormone is called leptin. And so when that hormone was discovered, it was found to have effects in the brain to increase how much energy you burn in a day, and to reduce your food intake. So it's kind of the way the body was having its set point. So, oh, there's a little too much body fat, boom, it feeds back, it tells you to eat less and burn more calories. And so this was thought to be the answer. This was gonna be the answer to the whole obesity epidemic. Because we're gonna give leptin to people and they're gonna stop eating and it's all gonna go away. Unfortunately, humans, as they gain weight, just as you might think, they have more and more adipose tissue, they make more and more leptin. So they have plenty of leptin. So giving them more doesn't do you any good. So that didn't pan out, and some companies spent billions of dollars to find that out, unfortunately. And there are other hormones that tell us about what our body is doing in terms of how much body fat and et cetera it has. But it's much more complicated, and we have short-term signals that come from our intestinal tract. So yes, our intestinal tract does have something to do with how much we eat, even though it's our brains that tell us to do it. There's a hormone called ghrelin that comes from your stomach that goes down when you start eating, and that's thought to be a hunger hormone. So levels are high before you eat when you're hungry, they go down when you start eating, and therefore you're not as hungry anymore. Hormones PYY, GLP-1 are hormones that come from your intestinal tract, and they start rising after you eat, and they feed back to your brain to tell you you're full. So they're satiety hormones, and these hormones, again, are very effective at doing these things, and certainly we have one treatment for obesity that is basically giving a form of GLP-1. All right, so if the system works, we overeat, that puts us in what we call positive energy balance. So we got to store that energy, and we store it as fat. So we gain weight, and we gain fat. So now we make more leptin, and we impact other signals. That should feed back to our brain to tell us to stop overeating, right? Unfortunately, that ain't happening right? Okay, that's not happening in an effective way in most of us. So why is that? So our biologic signals, again, are primarily designed to protect us from undernutrition is one of those issues. We might become resistant to these hormones is one theory, with the example that we make too much leptin, and leptin therefore is no longer having an effect on satiety and hunger and that kind of thing. So we become resistant to it to some degree. But maybe it's a lot more complicated than that. So we have these non-physiologic things that are important. We have internal, within our brain, inputs, reward, cravings, thinking about food, restraint, learned behaviors, attention. These are all really important. But then we also have the external environment around us. So the sight of food, right? That's why the food industry advertises. They know that when we see it, we're going to want to eat it. But that's important because when we, as an organism, we see it, we know it's there, it's available, we should go eat it. The smell of food. Who's gone to the mall? What's the first thing you smell? Cinnabon, right? They know that that's going to get you, right? And it's going to take all the restraint in the world to keep you from going over there. And then taste, ultimately, is a powerful signal as well. We know that availability and portion sizes affects how much you eat. If I put a bowl of candy at each of your little tables here, I guarantee it you will eat them because it's sitting there. If it's not there, you're not going to eat it. So availability is a powerful thing. Portion size. The bigger the portion we put in front of you, the more you're likely to eat. So these are things that are external to you that are affecting how much you eat. The social context. Some people eat more when they're hungry. Some people eat more when they're alone. Time cues. It's almost 7 o'clock. It's dinner time. I'm not even hungry, but it's 7. Our work schedules dictate that. We know we get a break, so we have to eat, even if we're not hungry. So time cues are important as well. So this is the model that we've kind of developed, is that on one side you have the physiology, fat-related signals like leptin. We have actual fuels, so glucose or sugar or fats in the brain telling us to eat more or less. Intestinal hormones. Distension of your stomach has an impact. And all these go to a part of the brain called the hypothalamus, and they control whether you eat or don't eat. But we also have, on the other side, these other signals that are non-physiologic. Internal and internal and external inputs. And they likely drive you to eat directly. So last Thursday, Thanksgiving Day, is the best example. You ate and you were full. So your physiologic signals were telling you to stop eating. And so you were like, oh, I don't feel so good anymore. Oh, why did I eat so much? But then comes out Aunt Dot's apple pie. And you've been waiting for Aunt Dot's apple pie all year. And you're going to eat Aunt Dot's apple pie because you know it tastes good, right? And so that's eating outside of your biology, 100%, completely driven this way. But it's actually probably a lot more complex as work from in animal models and some stuff we do in humans, that there's interactions between these things and these things across the brain, so it really gets complicated. All right, but I believe that these non-physiologic signals are actually too powerful for our biologic signals, because our biology is really not designed to be in this environment, and that's part of the problem. All right, so we're interested in the brain. If I was a rat scientist, it'd be easy. I could just take a brain out of the rat and cut it up and look and see where things are happening. I do humans, and I can't take their brains out or do biopsies. And so we want to think of, are there other ways we can look at the brain to see what's happening in terms of body weight regulation? And so we can do imaging of the brain, right? So we can look at anatomy using CAT scans or MRIs, but we can look at brain activity. Usually it's looking either, well, EEG, which is at the surface of the brain, is looking at electrical activity, but we're interested in what's happening internally in the brain, and so we want to look at blood flow changes which equate to changes in the nerves of the brain. So there are many ways to do this, and we use a tool called functional MRI. So it's a typical MRI machine, but we're looking at changes in blood flow in the brain using MRI technology. So it works like this. So you have a person in the MRI scanner, and they have this beautiful little brain, and we want to try to stimulate it. And we want to see, when we stimulate the brain, what parts of the brain lights up. And so what we can do is we can show pictures of yummy food. And that's what we do. And that will stimulate parts of the brain. We can have them smell the food. We don't do this. It's very complex, but there are people who do that. Taste, and we've done taste, at least sweet taste, certainly can be done as well. Now, you can't eat in the MRI scanner because head movement has to be kept to zero, and so chewing is going to cause problems. So we can stimulate the brain with direct food signals. We can have people think about food, and that's, do you really know they're thinking about it? We can ask them to do some tasks in the MRI scanners that relate to food or eating behaviors, things that relate to attention and impulsivity, for example. We use visual stimuli because we think that the first thing is seeing the food and knowing it's available. That's the most important signal. So we've used a model of looking at highly palatable, what we call hedonic foods, and compare them mainly to neutral objects that are not food related, but also look at times at low-calorie foods as well. All right, so I'm going to show you some pictures of the brain. These are kind of fun. And don't worry about this stuff. It's just to give you examples, all right? So we want to know, in a normal weight person, what does their brain do when we show them pictures of yummy foods? And to make it more robust, we make them fast and overnight so that they're hungry when they're coming to look at these foods. And what we see is that the brain lights up. So these orange, yellow blobs are where there's increased activity in the brain when someone's looking at food. And this is an average of like 20, 30 people across those individuals. And so these specific brain regions don't really matter, but what we see is that this is consistent. We've done this in many studies, and colleagues across the world have done similar studies, see the same thing, is that the brain lights up when you see food. And it lights up in areas that relate to reward, motivation, attention, and memory. So these are all very important brain regions that are consistently turned on. Now, if I make people overeat, all that goes away. It's the same people, same brains. And now they see the pictures of food and nothing turns on. These, again, are normal weight people. So they're very sensitive to changes in their calories, and now all of a sudden those foods are no longer rewarding, motivating. They no longer care about those foods. Pretty interesting. So then we wanted to know, how do people who are at risk for weight gain, or people who already have gained weight, how do they compare to people who are normal weight, and are they different? And the answer is they're very different, as you might think. And again, this is complex stuff, but what I want to point out is one brain region. We have people who are thin, and they're fasting, and they have increased activity. We make them overeat, they have reduced activity. This is in the green. In the blue are people who are reduced obese. So these are people who were overweight or had obesity who had lost weight. We know they're going to regain that weight, so they're at high risk for weight gain. And we see is nothing changes. Their brain's not as active when they're fasting, and when they overeat, it doesn't go down, it trends to going up. So it's a very, very different response to lean or thin individuals. And we see this in people who are at risk for weight gain, people who have lost weight, people already overweight. It's pretty consistent that there's significant differences here. All right, so can we do anything about this? Is a question, right? If we can't do anything about it, it's kind of a so what, right? So can we do something about it? Well, I wouldn't be here if we couldn't do anything about it. So the first one is other investigators have looked, if we do a behavioral diet intervention, what does that do to the brain? And we see change. We see that brain activity decreases. That's a good thing in this context. And so again, it emphasizes the brain is plastic. It can change. It's not hardwired. You can change that activity. So this is just with a behavioral intervention. We did a 6-month study with my colleague Ed Melanson with exercise. And we did imaging before and after 6 months of exercise and found that there was significant change in the brain response to food signals. And so, significant change. These are the averages before, averages after. You see there's a wide range, but certainly overall there was a significant reduction in areas of reward and motivation to eat. So a good thing when you think about weight loss. And this correlated to the weight loss that these people had. So the more there was a change in the brain, the more they lost weight. Chicken or the egg, I can't tell you at this point. And this is what we're studying. If anybody wants to be in my study, let me know afterwards. Weight loss medicines. So we can change the biology, like we give medicines for depression that affects neurotransmitters that are important in mood disorders. We can give medications that impact appetite regulation. And what does it do? Here we have liraglutide, which is a drug sold as Saxenda for weight loss. We see significant changes in the brain with this drug. Naltrexone bupropion combination is sold as a drug called Contrave. Again, significant changes in the brain response. So we can alter the brain with different interventions. All right, so yes, there is hope. We can rewire the brain. A couple of minutes. Do I have a couple minutes? Or yeah, I have a couple of minutes. Okay. So I know there's a sponsor, is the Women's Health folks. And so the question is, are there differences between men and women? And obviously, we all know that there are differences between men and women. And so men, yes, have bigger brains, but women actually use their brains. And there are structural differences, and there's many, many differences. But certainly even with food-related signals, there are differences. And we found, and this is actually in press, about to be published, that women had significantly more activation to food images in reward centers. Right? So food seems to be more rewarding to women than it is to men. Might correlate with some of the craving literature out there that there's more cravings in women. And then what happens with aging is the anorexia of aging is well known, that as we get older, we lose sense of smell and taste. We have less hunger. We have reduced motivation and desire to eat and reduced variety, and people tend to lose weight. Yet, on the other hand, menopause is associated with weight gain. We just talked about that, right? And obesity rates are rising in older individuals at a high rate. So that goes against this whole anorexia of aging. But on the other hand, there's some data that says that being overweight might be protective as we get older. So it's sort of controversial. So we're doing a study. This is a little plug. So we're looking for qualified participants who are 65 or older who want to be in our study. I have flyers out front. So we are studying and doing these brain images and all that kind of cool stuff. So if anybody wants to do that. All right, so I'm going to wrap up with this, promise. What can she do? Back to our case, is her genetics and her biology certainly might be at fault and might favor nutrient storage, especially in the environment that we're in. So what can we do about that? We can alter her biologic signals. How? Some specific behavioral change. Exercise. I showed you, we can change the way the brain is wired with exercise. Medications work. Surgery. We know a big portion of gastric bypass surgery is manipulating hormones, which then impact appetite regulation. She may be insensitive to her environmental cues. part of the reason why she doesn't think she's eating anything, right? And so we really need to find strategies to help her interpret or deal with the external environment better. And then finally, her behaviors might be at fault and certainly are part of it. And certainly, again, we have to find the right behavior change for her. That may not be the same behavior change as needed for the next patient that we see. And then remember that it's one size doesn't fit all. All right, I just had a closing slide, so I'm going to stop here and then let no, I'm good. I think this is a good place to finish. All right, so thanks for your attention.
Our next speaker, and by the way, we'll have a question, again, questions and answers right after this. We'll have a panel, which I imagine will be pretty lively tonight. Our last speaker is Dr. Huntington Potter, who's professor and vice chair for basic research in the Department of Neurology at the University of Colorado. He's also the director of the Rocky Mountain Alzheimer's Disease Center at the CU Anschutz Medical Campus and the director of Alzheimer's disease programs for the Linda Cernick Institute for Down Syndrome. His lab seeks to identify and develop new therapies to stop Alzheimer's disease, to reverse its cognitive effects, and to ultimately cure the disease. Thank you, Dr. Potter.
Okay. Anyone who can't hear me, raise their hand. I know that makes no sense. Okay, so what I'm going to try to do today is to give you a sense of where we are in our understanding about a disease that in the 1950s, I understand, was hardly even mentioned in medical school and has become a clear fear factor for aging. All of our benefits from medical advances and healthy eating and everything else has allowed our age to increase before we get really ill, and that brings us into the age of risk for Alzheimer's disease. So if you look around the room, we'd all like to live to be 85 or so, maybe more, but if we all live to be 85, about half of us will have Alzheimer's, and the other half will be a caregiver. And the worst for this audience is that both the caregiver status and the patient status hits women the hardest. So they have greater tendency to get Alzheimer's disease, and they're more often the caregivers. So this is a catastrophe, obviously, and we and many scientists around the world are trying to figure out what it is that's giving us Alzheimer's disease and how can we halt it or even reverse it. So the story of Alzheimer's disease starts with this gentleman in 1907 who reported the clinical symptoms and then the pathology of the brain of this woman, Auguste Deter, who was the first reported case of Alzheimer's disease. Now, the dementia that is described in his couple-of-page paper is absolutely classic in the sense that you, your family, your doctors will recognize it immediately as Alzheimer's disease. The lady had a serious problem with short-term memory, developing new memories. If you told her something, she'd forget it immediately. As she developed the disease further, she began to get paranoid. She didn't recognize her family, her doctors, and again, that's classic Alzheimer's disease. But that by itself doesn't describe a new disorder. The new disorder came when Dr. Alzheimer was able to use a new staining system to stain slices of the brain after Auguste Deter died and describe the plaques and the tangles, which we'll talk about presently, that characterize Alzheimer's disease from then on. Now, for the next 70 years or so, Alzheimer's disease was considered extremely rare. As I said, barely mentioned in medical school. And the reason for that was twofold. One was that Alzheimer's disease was used to describe dementia of the Alzheimer type, plaques and tangles in the brain, that occurred in relatively young individuals, in their 50s, for instance. And Alzheimer's disease wasn't really applied to people who developed these kinds of disorders after the age of 60. And that was even considered a normal aspect of aging. But in the 1960s and early 70s, the pathologists, the geneticists, the clinicians got together and realized that the senile dementia was really Alzheimer's disease, but at a later age. And that combined them, so that increased the total number. And of course, we're living longer and getting better diagnosis. So there are many people who thought that dementia was a normal part of aging, and now that's recognized as a disease entity. It just happens to be extremely common. Okay, so what's happened now is that we have about 5 million people with Alzheimer's disease in the United States. That's expected to go up to about 14 million by 2050. The cost now is about $250 billion a year in the United States alone, and that's expected to go up to about $1 trillion a year in Medicare and Medicaid alone by 2050 if we don't solve the problem. So how do we solve the problem? Well, the first thing is to look for drugs that might help the brain work a little bit better. That was the first approach, and there are now 4 FDA-approved drugs for treatment of Alzheimer's disease. None of them work very well. And the reason is that they don't actually attack the disease. They only serve as a Band-Aid to help the neurons that are left work a little bit better. And so, for instance, this is a connection, we call it a synapse, between this nerve cell and that nerve cell. And the way for these nerve cells to communicate is for this nerve cell to release chemicals, which we call neurotransmitters, that carry a signal from this cell to that cell. And what these drugs do is help the nerve cells communicate a little bit better. That's all. So that isn't really a good way to solve a problem like Alzheimer's disease, but it does clinically delay the course of the disease by about a year. So if you can take them, and they are really well-tolerated drugs, it can buy you about a year, but that's it. So how are we going to try to figure out more about Alzheimer's disease to be able to attack it at its base? The first step is to recognize that, as I hinted, a lot of nerve cells have died in this brain from a person with Alzheimer's disease. And of course, without nerve cells, you can't think, you can't remember, and that's the essence of the clinical symptoms. But the plaques and the tangles, which Alzheimer himself described in 1907, must be part of the disease because they're present in everyone with Alzheimer's disease. And the question is, of course, how do they contribute to the neuronal cell death? Well, one obviously is this is a nerve cell and it's full of this neurofibrillary tangle. Well, that doesn't look very healthy, and indeed that's true. That nerve cell is probably destined to die. The question is why? Okay, so for a long time it was said that Alzheimer's disease could not be diagnosed until autopsy, which is kind of late to intervene. And that's, of course, partly because our clinical assessment of people with dementia was not very well developed. But it's gotten a lot better, and a good clinician, such as our memory disorders clinic here at CU Anschutz, Dr. Jonathan Woodcock heads that, and they can be sure of somebody who have dementia that they have Alzheimer's disease about 80 or 90% of the time. But it's tremendously helpful to be able to see the brain, specifically the plaques, and now just recently the tangles, in a living individual, and that's shown over here in red. This is a positron emission tomography with a special compound that sticks to the amyloid in the brain and can be detected. And this person has Alzheimer's disease because they have a lot of amyloid in the brain. This person does not have Alzheimer's disease, and they're relatively low in their amyloid. So that has told us a lot about the progression of the disease. And one of the conclusions, which is shown on this slide, is that Alzheimer's disease probably starts 20 years before the first clinical symptoms. So it's not really a disease of old age, it's a disease of all age, and it just is manifest in old age. So if we can see inside the brain of a person as they develop Alzheimer's disease, we see that the plaques and the brain vessel damage begins to occur even in the non-demented preclinical stage and reaches a maximum throughout the rest of the disease process. The tangles begin to come up a little later, the nerve cells begin to die a little bit later, and it's really not until severe or moderate Alzheimer's disease that we really lose a lot of nerve cells. So obviously, in order to treat this disease, we have to be able to develop biomarkers, diagnostics that can detect the development of the disease in this stage. And that's being tried in a number of areas. We can't really give everybody a PET scan because they're about $5,000 a piece. But we hope that there'll be blood biomarkers that will mimic that. So before I go on, I want to mention three things, which is that Alzheimer's disease comes in sort of three different forms. They all have the plaques and tangles, they all have the clinical symptoms, but the important thing is that most of it is what we call sporadic. It is partly genetic. About 60 or 70% of it is due to some kind of genetic influence, but that means also that about 30 or 40% is due to environment. Then there are a few individuals that have a purely genetic form of Alzheimer's disease. They can occur in the 50s, in the 40s, in the 30s, and even in the late 20s, depending upon the mutation. Those families have been the key to our current understanding of Alzheimer's disease. And then this special group of people who have Down syndrome all develop the pathology of Alzheimer's disease in their brains by the time they're 30 or 40. We'll talk about why, and they develop dementia by the time they're 50 or 60. So these two groups have really given us the insights that I'm about to tell you about. So the first step in those insights was to really identify what the amyloid in the middle of this plaque is consisted of. And George Glenner and Kenny Wong in 1984 were finally able to identify the major protein in these amyloid deposits. And this is the single letter code, D, A, E, F. No, there's not going to be a test at the end because I don't even know the particular sequence by heart. But this was the beginning of the biochemical and genetic approaches to Alzheimer's disease. Why? Well, because once you have that peptide, you could ask where it comes from. And it turns out, using reverse genetics, that the gene encoding that protein was identified by a number of different groups. And it turns out that it's not from Mars, it's not from a bacteria, it's not from a virus. It's actually a gene in every single one of your cells that makes that A-beta peptide in greater amounts in people with Alzheimer's disease. And the most interesting thing is that that gene, which we call the amyloid precursor protein gene, is on chromosome 21. Well, that explains why people with Down syndrome get Alzheimer's disease, because they have 3 copies of chromosome 21 instead of 2 copies like all the rest of us. That means they have 3 copies of the gene, they make more amyloid, they begin to develop those plaques in their teenage years, and it just accelerates because they have an extra copy of the gene. So that meant that that gene really was important. It wasn't just an accident that you have amyloid deposits. It really was probably part of the disease. That was reinforced by this family and some like it, which showed that every generation, if a person has Alzheimer's disease, about half their children get Alzheimer's disease. Person has Alzheimer's disease, half their children has Alzheimer's disease. And it turns out that that kind of inheritance in this particular family is due to a mutation in this gene. So by overexpressing the gene or having a mutation in the gene, you're guaranteed to get Alzheimer's disease. That means we better find out what it does. And we have a big hope that this mouse shown here is going to give us that indication. Mice normally don't get Alzheimer's disease. The only animals that normally get Alzheimer's disease are monkeys, which are rather unethical and expensive to use in large numbers, and polar bears, and I know the dean doesn't want a lot of polar bears around the lab. So it was very important to develop an animal model to begin to test drugs, and mice were given the human gene that caused Alzheimer's disease in that family, and now the mouse gets plaques, gets a pathology of Alzheimer's disease. That's called a transgenic mouse. It's part human, well, one gene, and doesn't have any rights as far as I know. And that mouse gets the plaques, and that mouse also has dementia because it can't find its way around the mazes in the lab. So the ideas in the lab are tested first, and then they're put into activity in this mouse. We test the mouse for treatment with drugs, and it turns out that in this water pool with little channels, The mouse, if they ever get on this little platform, which is a little glass platform underneath the water, the mouse can't see it, but once they get on the platform, they're happy, and they can find the platform again if they're a normal mouse. But if they have Alzheimer's disease plaques, they can't find that platform. So there's a perfect system for testing new drugs, and that's what we're doing, and we're also testing whether that mouse can give us insights about Down syndrome at the same time. Okay, so here's one way in which we can cure Alzheimer's disease in the mice. It turns out that there's an important gene which, when in the ApoE4 form, it's called the ApoE gene, gives people an increased risk of Alzheimer's disease. If you inherit it from one of your parents, you got a 3-fold increased risk. If you inherit this ApoE4 gene from each of your parents, so you have 2 copies now, you have a 15-fold increased risk of Alzheimer's disease. It's a very important gene, and if we take it out of the mouse genetically, the mouse doesn't get amyloid deposits and has no trouble finding that platform. So if we could just get rid of the ApoE gene from each of us, we'd never get Alzheimer's. Problem is, it's kind of important. So we can't do that, but we could begin to ask how we could block the effect of ApoE, and that's one of the approaches for Alzheimer's disease drug development. So if we take all this and we ask, that's the genetics, that's great, but changing genetics is not so easy. One of the ways that we could approach Alzheimer's disease is to look at the environment. And it turns out that environment probably counts for about 30 or 40% of the risk. One of the ways that we can test that is to put that mouse in a typical mouse cage, which is shown here. And this mouse has food and water until, now or soon. It has Obamacare. It's treated better than most humans on this planet, but because it has that mutation, it gets Alzheimer's disease. However, if we put the same mouse into the Club Med cage, where there's toys and other mice to play with and running wheels for exercise and little mazes, they don't get Alzheimer's disease. They still have the mutation, they still make A-beta peptide, but for some reason or other, they don't develop the cognitive disorders. So what is it about this Club Med cage which is important? Turns out the most important thing is the exercise wheel. So constant, daily, or at least weekly, lifelong exercise reduces the risk of Alzheimer's disease in the animal and in people. So environment is controllable, and that's one of the ways that we can do it. So what are the environmental risk factors for Alzheimer's disease that we know about now? First, increased risk. High blood pressure, stroke, high cholesterol, those are all bad for you for many reasons. You remember the sort of subtitle of this set of lectures, brain, heart, and hormones. Well, anything that's good for your heart is probably good for your brain as well. And that means exercise, for example, lowering your cholesterol, lowering your blood pressure. It's a double benefit. Smoking. Smoking increases the risk of Alzheimer's disease by about 2-fold. So it's also bad for your heart. Get rid of it. Diabetes. Type 2 diabetes increases the risk of Alzheimer's disease about 2-fold. And so people who are obese, high cholesterol, high blood pressure, metabolic syndrome, they have an increased risk of diabetes and increased risk of Alzheimer's disease. Low educational attainment. Yeah, coming to lectures like this is good for you because your brain is stimulated, you make more synapses, and essentially what happens is you get increased brain reserve. And so when the nerve cells and those synapses begin to die, there are more of them to start with, and so you have a slower development of Alzheimer's disease. High BMI in midlife, and relevant to this one, female gender. It's not just that females live longer, that's part of it, but it seems that they have a propensity for Alzheimer's disease that is independent of the fact they live longer. And part of it, as we'll talk about, seems to be the loss of estrogen at menopause. So men also lose testosterone, as you undoubtedly know, with age, and that also increases their risk for Alzheimer's disease, but the effect is much higher in women. Decreased risk, I've mentioned exercise. Turns out that caffeine is also a way to reduce your risk. If you drink 3 to 5 cups of coffee a day in middle age, you have about a 60% reduced risk of Alzheimer's disease. Hey, that's good. Was there coffee out there tonight? Probably decaf. So we fed caffeine to the mice, and they get better. They have no trouble finding the platform after we've treated them with caffeine. Even decaffeinated coffee helps the mice a little bit. We don't know what those molecules are. Cognitive activity, as I said, coming to lectures like this, that's also reduces your risk for Alzheimer's disease. Okay, now what about these hormones? Obviously, at menopause, there's a reduction in estrogen, and that does, in the mice, increase their risk of developing Alzheimer's disease. And it can be replaced by hormone replacement therapy in the mice. And the data seem to indicate that women who had hormone replacement therapy fairly soon in their menopause experience have a reduced risk of Alzheimer's disease. But later, it's too late. You can't treat somebody with Alzheimer's disease with estrogen, male or female, and help them reduce their development of Alzheimer's disease. So it has to be started early. And there's been a little tiny bit of confusion because in the early days, estrogen was the hormone replacement, and that had a benefit for the long-term development of Alzheimer's disease. But later, hormone replacement therapies that included other hormones like progestin, that seemed not to have the effect. And that is experienced in the mice as well, because estrogen seemed to help and progesterone seemed to hurt. So that isn't necessarily a good approach to solving the problem of Alzheimer's disease, but it tells us a little bit about what might be going on in the brain. And as I mentioned, loss of testosterone also increases the risk for Alzheimer's disease in men and in women, and that can be obviated by testosterone therapy. And what we see in the animals and in the cells is that we have increased beta amyloid with these two hormones being reduced. So that probably explains why there's an increased risk for Alzheimer's disease. Now I'm going to talk a little bit about Down syndrome because that's my favorite topic. It's given us a lot of insights about Alzheimer's disease. And I was sitting in an audience similar to this, probably about this time of night. I was beginning to fall asleep. It was in the New Hampshire woods at a retreat for the MD PhD students, and somebody was talking about chromosomes. And it suddenly occurred to me that maybe what was happening in Alzheimer's disease, typical Alzheimer's disease, was that over the course of their life, their cells occasionally made a mistake. And instead of dividing into two equal daughter cells, that's the only female chauvinist title I know about in science. They're called daughter cells and not son cells. God knows why. But anyway, those daughter cells are supposed to get the same number of chromosomes as the parent cell, as a mother cell. And sometimes they don't. Sometimes a mistake occurs and they get the wrong number of chromosomes, and they usually die. But a cell that gets 3 copies of chromosome 21 instead of 2 is a perfectly healthy cell. You can live to be 60 years old with 3 copies of chromosome 21 in every cell. And so the idea was that maybe this accumulates over time, and the people with Alzheimer's disease are just mosaic, partial Down syndrome. They weren't born that way, but they developed over the course of life. So I had a Christmas vacation with a little bit extra time, and I wrote a theoretical paper suggesting that Alzheimer's disease and Down syndrome were all due to trisomy 21, so-called 3 copies of chromosome 21. So I came back, and I sent it off to a journal, and I got a 4-line rejection. The last line was, I wouldn't recommend publishing this manuscript anywhere at any time. So we published it in a different journal and spent the next 10, 15 years testing the idea, and it turns out to be correct. So how do we test that? Well, we can make a karyotype like this and count chromosomes, color them in various ways, and this person has 3 copies of chromosome 21 in this cell. And the other way we can do it is to use a fluorescent dye to label chromosomes, and this cell has 2 copies of chromosome 21. So by taking skin cells from people with Alzheimer's disease and asking how many chromosomes they have, it turns out that every type of Alzheimer's disease, both sporadic and various kinds of familial genetic forms, all have about 5% of their cells with 3 copies of chromosome 21 instead of 2 copies. Well, that was amazing. And the question, of course, is what about the brain? Well, it turns out that several labs, including ours, have looked at the brain cells in people with Alzheimer's disease, and it turns out that both nerve cells and non-nerve cells, it's about 8 to 10% of the cells in the brain have 3 copies of chromosome 21 instead of 2 copies. So they're partially Down syndrome. So the idea is right. The question is, how do we try to prevent that? And what about these other chromosomes? Well, there's more cells with the wrong number of chromosome 1, more cells with the wrong number of chromosome 7, et cetera. So lots of mistakes have happened over the course of the life of the individual that develop cells with the wrong number of chromosomes. So we're developing drugs to try to prevent that from happening. We have some that look hopeful, and they would have to be started early, of course, but they might prevent the development of these cells. So I've been talking about a group of people with Down syndrome who almost all get Alzheimer's disease, and people with a genetic mutation that all get Alzheimer's disease. But what about if there were a group of people who never got Alzheimer's disease? Wouldn't that be useful to know? And it turns out that people with rheumatoid arthritis very seldom get Alzheimer's disease. There are examples, but they're about 8-fold protected. And the idea, when that was discovered about 20 years ago, was that people with rheumatoid arthritis take a lot of drugs, anti-inflammatory drugs, to block the pain and the swelling and the inflammation in their joints. And we and others had shown that inflammation was an important part of the disease process. If you didn't have any inflammation in the brain, you would never get Alzheimer's disease. So the idea was maybe some of these drugs that these people are taking is inadvertently protecting them against Alzheimer's disease. So the NIH got together a bunch of scientists, it's about $500 million, testing the non-steroidal anti-inflammatory drugs in people with Alzheimer's disease, and it didn't work. So they said, well, remember, Alzheimer's disease starts many years before the clinical symptoms. Maybe we should start earlier in the, say, mild cognitive impairment stage, and it still didn't work. In fact, some people got worse instead of better. It was a great idea. The mice data suggested that it might work, but it didn't work. So I had a different idea, which was that maybe people with rheumatoid arthritis are reacting to this disease by generating differences in their blood. And maybe those differences, like a new protein or more of a protein or less of a protein, was protecting them against Alzheimer's disease by accident. So Tim Boyd, who was one of the students in one of those first slides, was a first-year graduate student, wanted a project. I said, go into the library and make me a big, long list of everything that's different about the blood of people with rheumatoid arthritis. And the list was pretty long, and we had to think about it, and we did some experiments, and many of them failed, but eventually we were able to find one protein which is up in people with rheumatoid arthritis, which when we injected it in this side of the brain of a mouse with Alzheimer's disease, and then ordinary salt water into this side of the brain, and waited 1 week, almost half the amyloid was gone from this side of the brain. One injection, 1 week later. That's the fastest reduction of amyloid that we or anybody else had seen. And the interesting thing is that this drug can get across from the blood into the brain. And so the next experiment was we injected it under the skin, and we asked what happens to the cognition of the mice. And it turns out they had no trouble finding the platform after a couple of weeks of treatment. So this was a way to treat mice with a drug, GM-CSF, granulocyte macrophage colony stimulating factor. Now, I didn't give you that name to get you irritated. Granulocytes and macrophages are like little Pac-Men. They go around the body and they eat up things that aren't supposed to be there. And what's not supposed to be there? The amyloid deposits. So that's why we tried it, and we think that's why it worked. So the mice get better cognitively, they get better pathologically, and GM-CSF is a very well-known protein. In fact, it's already an FDA-approved human drug. not for Alzheimer's disease, but for people who need their white blood cells, those macrophages and granulocytes, to increase. Like if you need a bone marrow transplant because you have leukemia, they give you very high doses of chemotherapy, kill off your bone marrow, and give you a bone marrow transplant. In order to help the bone marrow transplant get going, they give people GM-CSF to increase their white blood cell counts. And it turns out that we also looked at those people, and it turned out that they actually get better in their memory, in their cognition. The chemo brain that they get from getting the high-dose chemotherapy goes away faster if they get treated with GM-CSF. And the reason they can be treated is because, as I say, it's a human drug. It's called Leukine. And so that allowed us to do a Leukine trial on people with Alzheimer's disease. We started it down in Florida before we came here. We've continued it here. And the current trial is 3 weeks long, 5 Leukine injections per week for 3 weeks. And so far, we have looked at about 20 subjects. Another 10 we haven't looked at yet, but we finished the treatment. We don't see any adverse events. And that's actually very important because there are a lot of drugs that have been developed for attacking the amyloid in Alzheimer's disease, and all of them give microhemorrhages, little bleeding into the brain, that's not good, and swelling of the brain, and that's not good. But this doesn't show any adverse events like that. And there's a hint in the 3 weeks of treatment of people getting a little bit better compared to the placebo, and even compared to where they started. Then they decay when they take the drug away. So that's a hint, and it gave us confidence to apply for some money from the Alzheimer's Association, and they recently gave us about $1 million for a 6-month trial, and we'll start that probably in the new year. So it's a promising drug. It's not guaranteed. It's very, very preliminary, but we're hopeful that this will be one of the new drugs for Alzheimer's disease. Obviously, we're very appreciative of all the scientists and the clinicians who are involved in this, all of the funding that is necessary for this kind of work, and the participants in our trial. And we hope that we can be proud in a few years to say that Colorado helped develop a treatment that changed this red line, this catastrophe, into this green line. And I thank you very much.
Thank you so much, all three of you. Absolutely fascinating and hope-giving. I have a question for you, Dr. Potter. Recent other research suggests that there's actually 23, I believe it was, causes for Alzheimer's, and has suggested that they also have got a cure, which involves many different things. One of the important things in there is diet. And there has been no mention of diet at all tonight, specifically a plant-based diet. Could you comment on that, please?
I don't know whether this works. Yes, it does. Okay, so the only thing I mentioned about diet was caffeine, obviously. And it is true that the MIND diet, which is a sort of a modified Mediterranean diet with, fish instead of meat, and legumes and fruit and vegetables, and little in the way of dairy, does seem to have a benefit in terms of lowering your cholesterol, lowering your blood pressure, and we know that that's good in general. The other thing that Bredesen has put into that book and into his proposal is lots and lots and lots of exercise, which of course we all knew. So basically what he did was he took everything that everybody knew and tried to induce it to be taken by or abided by a number of people, and they did seem to get a little bit better. The caveat from a scientist's point of view is that anyone who has got the willpower to abide by that diet and that amount of exercise has already got a brain that's different than the rest of us. So this is not a scalable, intervention. You're not going to get 5 million people to abide by this, I'm sorry. And so what we sort of joke is that what we need is a couch potato pill that will help us get rid of Alzheimer's disease without all of this extra intervention. Yeah, good question. Now, as far as other diets are concerned, there are many sort of over-the-counter drugs that have been touted as potential Alzheimer's disease therapies. I'll just give you one example because there's not enough money to test all of them. But ginkgo biloba is a Chinese drug that has been touted for thousands of years as beneficial for everything. Not everything, but many things, including cognition. So another $500 million was spent getting the very best natural, organic, Chinese ginkgo biloba and do a clinical trial, and it had no effect whatsoever. So I'm not saying that diet is not going to be a very important component, but it's probably not going to be the panacea. Okay.
Thank you.
Yes, thank you so much for all three of you. This has been great. I do have a question for Dr. Potter. Is it possible that someone could still become a part of the 6-month trial? And is there a certain age that you're looking for to be a part of that trial?
Okay, so the question is there an age for entry into the trial, the 6-month trial, and what are the criteria? So the criteria are fairly stringent. We want a very special sort of intermediate stage group of people that aren't too far gone, so to speak, and aren't at the very early stages, because we want to make sure that we can detect whether they get better or if they get worse. So they got to be sort of right in the middle. And the other thing, of course, is that they can't have a pacemaker because they got to do an MRI. They can't have any other serious medical issues, et cetera, et cetera. So it's not for everyone. But it's available, and we recommend people consider it. But there are many other clinical research trials and interventions and observational studies that we have at the Memory Disorders Clinic. And so if you have someone or yourself that you really want to worry about your memory, the first thing to do is to get assessed, and then the potential to participate in research can be offered.
This is for all three members of the panel, depending on your expertise and whether you have any knowledge or have done any research in the areas. I haven't heard any mention of the effects of alcohol or other drug use on any of the conditions that you've spoken to tonight. So I was just curious if there's anything related to that.
Thank you for bringing that up. That's a really good point. With respect to menopause, there's a couple of things that are actually are known. One is that alcohol tends to make your hot flashes worse and makes you sleep worse, yet it seems like a really good idea when you want to go to sleep, and it doesn't really do the trick. And so generally good to avoid or limit it. The other thing that's important to know about menopausal symptoms is one of the things that I've learned when studying a group of women, half of whom used street drugs to go through menopause, is that they can mistake menopausal symptoms for drug withdrawal and actually step up their use of street drugs. So it's something to keep in mind, when we're taking care of patients, is to ask those questions of people and make sure that you have a grip on that. But those things will change the menopause experience.
In terms of body weight regulation, well, alcohol has calories, so we can talk about other drugs of substance, of abuse. They don't have calories, right? But alcohol does, and actually alcohol has, intermediate between carbs and fat. So it has 7 calories per gram versus 4 for carbs or 9 for fat. So it's part of the energy balance equation that if you consume a lot of alcohol, you're consuming more calories. On the other hand, though, if you look at population studies, people who drink more aren't necessarily more overweight. So there's a little bit of a paradox there. We do know that people who suffer from alcoholism, who drink in excess, really actually have malnutrition and lose weight. So at the end of the day, I think we have to remember that alcohol has calories, and we have to consider that when we're thinking about how many calories need to come in and out when we're trying to lose weight. The other thing, for some individuals, you have a drink or two, you lose inhibition, you might be more apt to eat. On the other hand, not everyone, I think, is that way either. The other thing is there's been a lot in the literature about food as an addictive substance. And certainly, if you look at brain scans that relate to cocaine use, they look a lot like the images I showed you with food stimuli. And so certainly we don't want to say that food is addictive because you have to eat, right? And there's no withdrawal if you don't eat. So it's not by definition an addictive substance, but it certainly has many properties that act like other drugs in terms of addiction. So that's
one of the worries that we have in the clinic is that there are too many people being treated for Alzheimer's disease with those 4 standard drugs by their primary care physician without the proper workup to find out whether they really have Alzheimer's disease or not. Alzheimer's disease is the primary cause of dementia in the elderly, probably about 70%, but that means 30% is not Alzheimer's disease. And in one case, like frontal temporal dementia, which is a sort of second or third most common cause of dementia, those drugs can be damaging. It can make things worse. So it's very important to get appropriate diagnostic. And one of the things that can give you dementia is Wernicke-Korsakoff syndrome, which is caused by alcoholism and the loss of vitamin B due to taking your calories as alcohol. And that can give you a dementia as well. So excess alcohol is definitely not good for dementia. A little bit, at least in the mice, might be okay, but it's only a little bit. And red wine has some molecules in it that may be helpful, at least in the mice, but the data in humans are not clear yet.
make one more comment. Because alcohol has calories, the body does sense those calories. And so there are some evidence in animals studies that they sense those calories and they eat less food, so they don't necessarily gain weight. And we did a study in women, 10 weeks of 2 glasses of wine versus 10 weeks of no wine. Some people loved it, some people hated it. And there was no weight difference at the end of 10 weeks of 2 additional glasses of wine. So they obviously compensated. So I think it gets pretty complicated when you think about it.
I have a question for all three of you. The role of estrogen was woven throughout all three in all three of your talks. I'd like to hear from each of you about estrogen in terms of, is it just the loss of estrogen that causes all these things? How important is the role of estrogen in Alzheimer's? How important is the loss of estrogen in the weight gain? And how important is the loss of estrogen for other menopausal symptoms?
A couple of ways to look at estrogen. You give it, you take it away. I call it the hormone hokey pokey when you're looking at men versus women, or you can always do those types of experiments. And there's clear effects when you take estrogen away from women experimentally by giving them a GnRH agonist, a medication called Lupron. How many of you heard of that? It just takes away your estrogen, gives you a medical menopause. You do see changes in sleep. You sometimes see some changes in metabolism, but there's another way that you can mess with hormones in the brain, and that's by taking away the receptor. And if you alter the estrogen receptor in the brain, all kinds of stuff happens. And if you alter it in certain regions of the hypothalamus, again, where Dr. Cornier was talking about central to regulating a lot of these body functions, you can create a mouse that does not want to move, that eats more. I don't know if you can look at the hot flashes in the mouse, but it seems like it's created a complex that's somewhat like what happens in menopause. So there's clearly effects in some of those centers of the brain. It's just not well worked out right now exactly how that all interacts.
There's evidence that estrogen impacts leptin signaling in the brain. And we know that leptin is important for body weight regulation. So interestingly, though, estrogen seems to be associated with more leptin sensitivity. So if you think about that, if you're more leptin sensitive, then you should have more satiety when there's more leptin around. Yet we see that women tend to have more reward and cravings and those kind of things. So it's not clear cut there. Our colleagues, Dr. McLean and others, have done studies with exercise in animals and found that exercise helps with weight regain. After weight, like get their little rats to lose some weight, and then if they exercise, they don't regain as much weight as those who don't exercise. Well, they went back and said, well, no, that only happened in the male rats. They did it in the female rats, and the exercise didn't help them at all. And so then they took their ovaries out of the female rats, got rid of the estrogen, and now the female rats acted just like the male rats. So there seemed to clearly be an estrogen effect of how the body was responding to exercise from body weight and food intake. And their hypothesis is this relates to leptin sensitivity to some degree. So obviously it's an important hormone, estrogen that is, and in this whole puzzle, but exactly the role is not clear, because as we give estrogen back, it doesn't necessarily cause weight loss.
Yeah, the work in Alzheimer's disease is kind of similar. You take estrogen away, and the female mice get more amyloid and get demented faster, and it can be replaced by artificial, estrogen. But the whole set of steps in the pathway from estrogen to amyloid to dementia is still being worked out.
I have a question about a hormone that has not been mentioned tonight, the I hormone, insulin, and Dr. Santoro, how it might affect women with menopausal issues, the fluctuation of insulin. Dr. Cornier, how to maintain weight loss or to achieve weight loss with steady insulin, and the effect of insulin on memory.
Good questions. Not really good answers for them either, Gina, sorry. For women that have metabolic syndrome, they're hyperinsulinemic, and if you can make them more insulin sensitive, that will help. I will tell you a personal story that blew me away, because when I was going through my menopause, the seven dwarves lived with me, shall we say, for several years. And I was certain that I was having these wild fluctuations in blood sugar to the point where I was keeping like little candies around and eating them when I just didn't, because you just feel crummy, you just don't know why. And I was absolutely attributing this to my blood sugar. I thought I had it all worked out. And then I made the mistake of doing one of my own studies where we did a mixed meal tolerance test, because I was working with Dan Stein at Einstein at the time, and we were looking at glucagon and insulin changes, and did insulin sensitivity change with or without hormones. And I watched my glucose while I ate this this caloric meal, and for the next 6 hours, and my glucose did not budge. It stayed, it was like 78 the entire time. And this whole time I was going through the highs and lows and the agony and the ecstasy of all of my illusions of what my blood sugar was. And I was just dead wrong. So I just think we have, and many of my patients will come in with menopausal symptoms and say, and I know I'm hypoglycemic, I know it. So I would say be super skeptical about that stuff and just measure as much as you can, because I myself was just amazed. And I would have sworn to you with confidence what those results would have been. If I am a betting woman, you could have taken my money that day.
Nice story. Insulin is a tough one. It does a lot of interesting things. So its primary goal or role is to help you store fuel in your body, right? So insulin helps drive glucose into your cells, and it helps suppress breakdown of fat. So that's the main things that it does. So when you eat a meal, you get a surge of insulin that's there to push the sugar that you just ate into your cells, and you don't want to be breaking down fat when you're eating to help store more fat. So it's an anabolic hormone. On the other hand, if I inject insulin into your brain, you will eat less. And so people think that insulin makes you hungry. It doesn't make you hungry unless it makes you hypoglycemic. Then that makes you hungry. So insulin, when we use insulin to treat patients with diabetes, it certainly can cause some weight gain because it's an anabolic hormone. But it doesn't cause people to be hungry per se. So what's more controversial is, I'm not exactly sure where your question's going with this. Does it relate to glycemic index? Okay. So one is, I'll be honest, I'm not a fan of the glycemic index, because we don't eat glycemic index. We eat mixed foods. And the glycemic index was developed by what does your blood sugar do with a piece of bread, and then they compare it to other things, right? We don't eat just a piece of bread. We eat bread with peanut butter on it or with cheese. The minute you add fat and protein, it affects the absorption of the carbohydrate, and so you don't get the same peak. So people have talked about glycemic load, which also takes in consideration the amount, which is probably just as important as the property of the carbohydrate. And so glycemic load is a step in the right direction. But overall, I like to consider carbs more as high fiber versus low fiber, or grains versus simple, and not get into the glycemic index. But does eating foods with carbohydrates does cause your insulin go up? Is that a bad thing from a weight loss or a weight perspective? I don't think we know the answer to that. When you gain weight and you become more insulin resistant, then insulin doesn't work as well. So you make more insulin. So if you're resistant to insulin, then maybe you're not storing fat as well. So maybe that's protective, and that's a good thing to have insulin. Again, there's a lot of controversy there. So I'll leave you with an unanswered question.
Memory, yes. Well, I mentioned that type 2 diabetes is a risk factor for Alzheimer's disease. We don't know the mechanism, but many people have thought to call Alzheimer's disease type 3 diabetes. And the reason is that if you do a special brain scan and measure the glucose utilization in the brain of people with Alzheimer's disease, it's low. And one of the reasons seems to be that the cells have become resistant to insulin. We have some ideas and some experiments that suggest why, and maybe that would be a potential treatment. There has been, or at least a way to develop a treatment. There has been a clinical trial to have nasal insulin administered to people with Alzheimer's disease. The initial results seemed promising, but the follow-up results were not so promising. So it seems to be a bit of a frost.
One concern with that was that the nasal insulin causes reduced food intake. And we know that people with Alzheimer's have trouble because they don't remember to eat or not, right? So there's a lot of issues.
Yeah, and I think just to go back to your question about metabolism is that to me it's one of the tools in the toolbox is to consider if an insulin sensitizer will be helpful because it is for some women. There is a book written by an endocrinologist at New York Medical College, Harriet Mogul, and it's called Syndrome W, A Woman's Guide to Midlife Weight Gain. And she has a bunch of strategies that can be very helpful. I have had some patients do very well with it, others no effect at all. So it's just one of the other self-help tools that's out there.
I have a question. I think it's for Dr. Potter. Something you mentioned. How long after going through menopause would it be too late to consider the possibility of estrogen replacement therapy?
So the question is, how long after menopause should be the hormone replacement therapy thought about with respect to protecting against Alzheimer's disease? Well, I have to say I don't know because the hormone replacement therapy comes in various different forms, and the current form seems not to be so protective, so that doesn't seem necessarily a reason to take it. You should take it for your other health reasons, that it's not going to cure your Alzheimer's disease.
Well, I had a question about the caffeine intake you were talking about that helps to reduce Alzheimer's. Does that apply to people who drink lots of tea? I'm not a coffee drinker. So I wanted to know, as far as the protectiveness of caffeine, does that also apply to people who are tea drinkers?
So the question is, what about tea? The studies were done in a country, Finland, where tea was not drunk very much, so they don't have enough data to say about tea. In the mice, it was the caffeine that did it, and so we know caffeine helps. The amount of caffeine in tea is less than coffee, but inveterate tea drinkers often drink a lot more tea. The other possibility, of course, is 10 pounds of chocolate a day.
Thank you. Drive safely. Have a nice evening. Thank you very much for attending.